Good morning, afternoon, or evening, whenever you are watching this. We are in the optics laboratory in Monterrey, and today we're going to talk to you a little bit about the Stern-Gerlach experiment, and we have arranged an optical arrangement which illustrates the basic mechanics of the experiment. While it is not a direct analogy to the experiment, it is very easy to try to get an intuition for how the experiment works, looking at what we will show you here in a bit. In 1922, Otto Stern and Walter Gerlach were working as assistants in the University of Frankfurt, and they decided to design an experiment to test the ideas that were postulated by Bohr and Sommerfeld in their quantum theory. And their basic ideas, the main physics of the theory, was that for atomic systems, angular momentum in the orbital sense had to be quantized. So they decided to run an experiment using silver particles passed through a magnetic field which was spatially non-uniform, and they were expecting to see some deflections in the trajectory of the particles if Bohr and Sommerfeld were right. Bohr had initially postulated that the energy levels in an atom were quantized, and thus the electrons that were orbiting the nucleus of the atom, as if in a planetary system, only could occupy certain specific energetic states. So a consequence of this is that the angular momentum for each of these electrons in each of these orbitals also have to be quantized. And if this theory were correct, then the net orbital angular momentum for a silver atom, or any atom for that matter, would also be quantized. Normally, you would expect a magnetic moment to be associated with a net orbital angular momentum if you are dealing with electrons, because you have electrical charges which are moving in a circle and are producing a magnetic field as a result of that motion. That magnetic field has associated with a magnetic moment, which, if the angular momentum was quantized, the magnetic moment also had to be quantized in terms of the angular momentum. The interaction between this magnetic moment and the magnetic field that Stern and Gerlach ran the atoms through was that they were expecting the trajectories to deflect in different ways. And if classical theory were correct, they would have experienced a continuous distribution of incident atoms on the plate, because classical theory would predict that the magnetic moment would be randomly oriented. This is to say, for each inciting atom, the magnetic moment would have a different direction. But if Bohr and Sommerfeld were correct, the magnetic moment would necessarily have maybe perhaps not just one direction, but it would be quantized. So the fringe, well, not fringe, but the incidence pattern on the plate will show that. It would not be continuous, but it will be of a discrete nature.
This is set up for the Stern-Gerlach experiment. We have a furnace over here that produces a beam of silver particles that is passed through a collimator to make them all into a vertical beam, or horizontal beam, sorry, which passes through a non-homogeneous magnetic field produced by two pole pieces, which is pointed and the other one which is curved. The silver particles pass through the non-homogeneous magnetic field, and since it's variant in space along the z direction, force is produced, and the silver particles are deviated from their path, and the final deposition of the silver particles is noted on the screen. This is the experiment which Stern and Gerlach did, and which they used to find how the silver particles were deposited on the screen after doing the experiment. So, since we already know that the spin can only have one of two directions, it can either have spin up or spin down, and since the net spin has a certain direction made with the z-axis, we can say that these are how the spins orient as they're going through the magnetic field. Here is an illustration of how the magnetic field looks like. This is the pointed north pole piece, which produces a strong magnetic field at the top, and this is the south, where it's a lot more spread out. So there's obviously there's a difference in the magnetic field from the north and the south. From a class of electricity and magnetism, we know that the potential energy produced the potential energy of a magnet moving through a magnetic field is given by the dot product between the magnetic moment of the magnet that we're analyzing and the external magnetic field. To have a force, we know that it's the negative gradient of the potential field, field that we have. And when we do the derivative, we already know that this is a constant in the z direction. So we have the mu z component, which is 1/2 of h bar, and the derivative of the external field in the external magnetic field. Silver has a very curious electronic configuration, which is why it was used for this experiment. It has just one unpaired electron. The silver's electronic configuration, as we know all from our chemistry courses, is argon, followed by the 4d orbital, which is fully filled, and the 5s orbital, which has just one electron, which is unpaired, which means we have a net spin in the entire silver atom. And this spin can either be in the up or the down direction on the z-axis, depending on the orientation of the silver atom.
The classical prediction for the experiment was that because the directions of the magnetic moments of the atoms would be randomly distributed, there would be detected a continuous line of incidence upon the plate. So if we imagine that the light is the incidence of silver atoms, what we would detect is, metaphorically, a straight line. Each differential component of this line would correspond to a different orientation of the magnetic moment if it were randomly aligned, and if classical theory were correct, we would have observed a very similar result to this in the original Stern-Gerlach experiment. But it turns out that what they detected was something very different.
In this arrangement, we have a source of laser. This laser will be then translated to a light beam polarization that will translate the laser with a source of two mirrors and will lead into this apparatus, which it's kind of a half mirror. But normally what we will find in a half mirror is that we will find that the laser will be cut into two different lasers, one perpendicular and the other parallel. In this case, we don't have that type of thing, because this thing splits the laser into two different lasers, parallel lasers. If this were the Stern-Gerlach experiment, this laser will be the source of the silver atoms. These silver atoms will take the trajectory, and in this part where the beam splitter is, this will be the inhomogeneous magnetic field that will split the spins of the electrons. Finally, what we should observe is these 2 points on the screen.
It passes through.
So what we're watching here is an hydrogen atom with its orbitals, continuous phenomenon. If it were like that, we will see something like this. But the experiment shows us that it came up like this, showing that angular momentum was quantized. And, well, Stern-Gerlach some time later realized it was actually a known property of the particles called spin, which we now know kind of well.
Spin is an intrinsic property of the electron, which makes it have a magnetic moment, which is what causes the electron to have a net force while moving through the non-homogeneous magnetic field. What happens is, due to the spin of the electron, it generates a magnetic moment in a direction that's exactly opposite, and it forms a component with the external magnetic field, which is in this case the z direction, and thus we know that the z component of the spin is 1/2 of h bar, and we can say that this explains what occurs in the Stern-Gerlach experiment a lot better than the Bose-Sommerfeld theory, because we now know that there is a magnetic field, an external magnetic field, and we know that it has we can have two discrete directions, which would prove that spin has either up or down direction, far better than having a spatial quantization of angular momentum in an orbital. because angular momentum in an orbital would be spinning around in all directions, which means you wouldn't have just a single direction movement, you'll have a movement in more than one direction.
A happy coincidence is that right after Stern-Gerlach had started conducting the experiment, they were having difficulties detecting where the silver atoms were inciting on the plate. And as history would have it, Otto Stern had the custom of smoking very bad cigarettes. Very bad cigarettes in this context. Very bad cigarettes in this context means cigarettes which have a very high sulfur content. So, as a result of this, Otto Stern had a very high sulfur content on his breath. And as he approached the plate in frustration of not being able to see where the silver atoms were landing, the sulfur in his breath reacted with the silver that had accumulated on the plate from the previous experiments, and the reaction synthesized silver sulfide, which is black. And because of this, they were able to see black spots in the places where the silver atoms had been inciting. And it is funny to think about how maybe something that was very bad for his health, namely smoking bad cigarettes, turned out to be very good for physics. And that certainly wouldn't have happened in this laboratory.
An interesting property of spin can be observed if we look at several Stern-Gerlach experiments in sequence. We can take, for example, an original silver furnace, which will produce atoms going in this direction, and we can run it through a Stern-Gerlach apparatus, which produces a magnetic field which is non-uniform in space, and we can make this apparatus measure the C component of the spin for the unpaired electron in these silver atoms. So we will say that this is a SC apparatus. Naturally, this will produce two beams, one for spin up and one for spin down. Now, if we were to block one of these beams, we could keep only the spin up beam, which contains only the spin up component. Actually, this is the spin down. This is the magnetic moment up component. And we can run this beam through yet another Stern-Gerlach apparatus. But this time, we will do a measuring along the x-axis of the spin. This will produce another two beams, one corresponding to spin down in x and one corresponding to spin up in x. And the interesting feature of spin is that if we were to take this beam, we can block this once again, and we take this beam and we run it through yet one more time a Stern-Gerlach apparatus which measures the C component of the spin. Surprisingly, it will yield two beams, one for spin down and one for spin up. Now this is completely counterintuitive, because if you see the sequence of events, we produced the X beam that went into this apparatus using only a spin down beam from the C axis. So it would seem that the spin down beam in the C axis contains both spin down and spin up in its own axis, and that is completely counterintuitive. It seems like we were doing something wrong, but as a matter of fact, it turns out that we can only measure one component of spin at a time. This means that when I take a measurement on the C axis for spin, all my information on the X and Y axis gets destroyed. So I run it through a C apparatus and I obtain information about the C axis. Then I run it through an X apparatus and I destroy the information that I have obtained from this experiment, and I get information pertaining to the X axis, both for spin up and spin down. And then I run it through the C axis again and I destroy this information. So by virtue of having run the spin down beam in the C direction through an apparatus that measures the X component, it is as if I had never run the beam through the CA apparatus in the first place. We can only know one component of spin at a time. Each time we take a measurement on any of the three components, we destroy any information we might have regarding the other two components.
Porque eres
That's residue. And as we then casually lean onto
Eso va a salir en los bloopers.